All right, good afternoon, everyone. Thank you for being here. And I would like to go ahead before welcoming our distinguished speaker. I would like to talk a little bit about the Kent Seminar. The Kent Seminar series sponsored by Paul F. Kent Memorial Fund. And this fund was established in 1977 to support transportation engineering education. And the seminar is named after University of Illinois Urbana-Champaign Department of Civil Engineering alumnus Paul Kent. In 1920, he graduated from UIUC with civil engineering and held the highest regard for this department education that he received. He became a civic servant in Illinois and the surrounding states and was the founder and president of the University of Illinois Civil Engineering Alumni Association, which is the largest civil engineering alumni association, I guess, in the world. He was also the recipient of the University of Illinois Loyalty Award and the Civil Engineering Distinguished Alumnus Award. This semester, as you know, we had 14 presentations on transportation, and we were focusing on transportation and climate change and look into the innovative work that we have on green technologies and strategies for mitigating the impact of transportation on our changing climate. And of course, we're very, very pleased that our distinguished lecturer for this semester is Professor Yin. So Professor Yin is a professor and the Donald Mellu Department Chair of Civil and Environmental Engineering and a professor of Industrial and Operation Engineering at the University of Michigan in Ann Arbor, of course. He specialized in transportation system analysis and modeling. He has authored more than 150 refereed papers in leading academic journals. He holds a doctorate from the University of Tokyo and master's and bachelor's from Tsinghua University in Beijing. He's definitely is one of the top in his field, and we're very, very pleased to have you with us here. We have known each other for a while, and I'm glad and honored that we were introduced by Professor Ouyang. And since then, I guess I visited with him at University of Michigan too. And we're very, very pleased to have him with us to talk about transforming the transportation network equilibrium analysis paradigm via end-to-end learning. We're very pleased that you are with here today, and we are welcoming you to the University of Illinois.
Thank you, Professor Yin. Good afternoon, everyone. Thanks for being here. It's my great pleasure and my honor to give this distinguished lectures. So today I'd like to talk about one of our recent work on how to leverage machine learning to transform transition network equilibrium analysis paradigm. So this is a joint work with my PhD students, Justin Liu, and also two researchers from General Motors. So working with General Motors allow us to access their trajectory data to do an empirical study in the city of Ann Arbor. So this empirical study is still ongoing. So therefore, today, the numerical example I presented today will be based on synthesized data, not empirical data. So I'd like to also thank my sponsor, National Science Foundation, US DOT Region 5 UTC, Center for Connected Automated Transportation, and also General Motors. So here's the my plan for today. I will first give a very brief overview of the transition network equilibrium analysis paradigm and discuss why we want to transform the paradigm and how we're going to transform the paradigm. And then I'm going to use an example to demonstrate our proposal. And then also briefly present the results from our formal analysis. And then I conclude my talk with a few remarks. So I plan to finish my talk maybe within 40 minutes. Then I leave ample time for discussion. Okay. So as you know, transition network equilibrium modeling paradigm play a very important role in the planning and operation of transition networks. So in practice, when you try to improve the system performance, typically you have multiple options, a multiple plan and multiple designs. So we use this paradigm to compare different plans with an option to choose the better one for implementation, right? So to ensure fair comparison, we evaluate this performance, these options against a consistent benchmark, which is equilibrium state. So more specifically, we estimate the network performance on the option A at equilibrium state, and then compare with system performance under option B at equilibrium state, and then choose the better one, right? So this is to ensure apple to apple comparison. So the notion of the equilibrium is very critical in this paradigm. So this notion was introduced by John Wauchope in 1952. So that's why sometimes we call it Wauchope equilibrium, which refers to a network state where no traveler can improve their utility by unilaterally changing their travel choices. So Wauchope proposed this concept in 1952, which actually is a special case of Nash equilibrium proposed by John Nash in 1950. So this is a special case with in a game with infinite number of players. Okay, typically when you talk about Nash equilibrium, and you talk about a steady state with finite number of players. So when the number of players increases and computing the Nash becomes more challenging. However, if you look at the extreme, when the number of players become infinite, computing Wauchope turns out to be much easier. Sometimes as easy as solving a convex optimization problem, like the one proposed by Beckman, McGuire, and Winston in 1956. Okay, so this is a convex optimization under some mild conditions, and this concern about rule choices at a static level. And in this situation, Wauchope equilibrium refers to a state that for each OD pair, the multiple passes at steady state, the utilized path will have the same travel time, which is lower than or equal to those of the unutilized path. And the demand will be given by demand function. The argument with the demand function will be the equilibrium of the travel time. And certainly the flow has to satisfy all the flow constraints, right? So this is going to be the mathematical definition of Wauchope equilibrium in this situation. So the equivalence of this BMW formulation, Beckman, McGuire, Winston formulation, and this mathematical definition of Wauchope equilibrium can be established by checking the automatic condition of the BMW formulation, right? So this is really the seminal work, and this laid out the foundation for transition network equilibrium modeling paradigm. In the last 70 years, and this paradigm has been extended by multiple researchers, including myself and many others in the audience, to model other travel choices such as mode choice, destination choice, departure choice, and also capture within day and day-to-day traffic dynamics, right? So, and also the paradigm has been utilized to support the planning and operation of the system in this country and across the world. Okay, so this paradigm has been advanced substantially, and also this paradigm has enjoyed huge success. So why we still want to transform the paradigm? Okay, so there's multiple reasons why I want to transform the paradigm. Today I just focus one aspect, which is enhancing the behavioral realism. If you look at when you learn, I think for the BMW formulation, virtually every graduate student, continuing graduate student, has learned about that formulation. When you learn the formulation, your instructor, your faculty, your professor going to tell you that this formulation is based on a very strong assumption where you assume that traveler has perfect information, they're perfectly rational, they want to just minimize travel time, right? So we also argue that the choice behavior are much more complicated than that in reality. And that's the reason why significant effort has been made in the last 70 years to enhance the behavioral realism of equilibrium model by considering, for example, imperfect information, random utility, boundary rationality, and reference dependent, etc. Okay, because there's so many behavior models that you can select from, and then you can actually plot this behavioral model to build an equilibrium model, equilibrium models. So it's really a constant battle that researcher modeler has been fighting over the last 70 years. Many models have been proposed, but all those models have been constructed using a approach I call bottom-up approach. And the model building process starts like this. The first step, you have to choose a behavior model for choice preference. So let's assume you want to model rule choices. I decide to use multinomial logic model to model rule choice. Okay, you start from selecting a behavior model, and then you conceptualize that if everyone behaves this way, what is going to be the corresponding equilibrium state? And then you propose equilibrium condition to characterize that state, right? That's the next step. And for example, if we use multinomial logic model for rule choice, and the right-hand side is going to be the nonlinear system that define equilibrium state. And you get a nonlinear system, sometimes you get a nonlinear complementarity system. So solving the system is very difficult. But you can solve the system to get equilibrium flow distribution, but solving that is difficult. Then the next step is I will formulate an equivalent mathematical formulation. In rare cases, you can formulate, you get a convex program like the BMW formulations. And in general, you can now get a convex operation mathematical program, then you have to formulate as variational inequality, for example, the general formulation, or fixed points or nonlinear complementarity problems, right? So they're equivalent in a loose sense. And so that's assuming you formulate it as a variational inequality. So the variational inequality goes like this. You have the generalized path cost, the inner product, and the feasible path flow minus the equilibrium path flow, the inner product is non-negative, right? That's the typically variational inequality you get. And if you use multinomial logic model, and that cost function, the generalized path cost function will be equal to the path travel time plus 1 over theta log path flow. Okay. The key point here is if I choose the different behavior model, I will have a different generalized cost function. The generalized cost function is going to be different. Okay. And sometimes if your behavior model is very complicated, you don't even have a closed form expression for that cost function. So once you have the VI and you know that there's a standard solution algorithm available to solve VI, you just choose one of them and you can solve the VI to prescribe the equilibrium, link flow, and travel time. And if you have empirical observation against that empirical observation, you can calibrate the parameter in the behavior model. And that's going to be the theta in this case. That's the modeling process. And all those models are built based on using this approach. So I call them bottom-up approach because you start from selecting a behavior model. So if you choose a different behavior model, you will have a different mathematical definition of your equilibrium state. You have different VI formulation, and the calibration process will be different. Okay? Because there's so many behavior models you have to choose from. And so why you choose a particular behavior model, for example, multinomial logic. The selection really is not from any calibration process because calibration happens after you make that selection. Okay? Because there's so many behavior models you choose from. The reason why you choose a particular behavior model simply because you believe that behavior model is a better behavior model, is a more realistic model, based on some lab experiment. And you believe that, right? So the key limitation of this approach is the selection of the behavior model is not data-driven. And the selection of the behavior model only reflects the modeler's belief or judgment that you think this behavior model is a better model. It's not the outcome of any calibration process against empirical data. So the selection really is detached or divorced from the ending goal of the model building, which is to prescribe an equilibrium flow distribution that match observation as closely as possible. That's the major limitation for the bottom-up approach. That's the limitation we try to address. Okay, so how are we going to address this limitation? Our proposal is to move from bottom up to end to end. Okay, so to facilitate the presentation or introduction of the idea, so let's think about a case. There's a planning agency is interested in developing a static network equilibrium model to analyze a traffic network for peak period. Okay, that's the scenario we're going to think about. And then assuming all the demand and link travel time, partial or all the link travel time can be observed for a long period of time. Okay, so imagine the network you are trying to analyze is the toll freeway network with ETC, electronic tolling systems. So this way, you know that the ramp-to-ramp demand, you can observe all a lot of link flow, etc. And for model building, we assume all the link performance function are known. And then now the learning task is to learn about the traveler route choice preference from multi-days of observation of link travel time and OD demand. Okay, we only had aggregate travel time observation and demand observation, and we really learn about those route choice preferences. Okay, so that's the task. Because you're trying to build a network equilibrium model, and so in general, you have a VI formulation, right? I mentioned that the inner product of the pass cost and feasible pass flow minus the equilibrium pass flow is non-negative. And I may also mention that if you choose a particular behavior model, and then you have a particular functional form for the pass cost. And now instead of pre-select a particular functional form, we're going to approximate this cost function using neural networks. And the neural network can allow us to achieve a much richer representation of the route choice preferences. Okay, we approximate this. And so now you will have a neural network-based VI formulation. And so now the X here is going to be the contact information. This is going to be input to the neural network, which I will introduce. And theta here is going to be the weight for the neural network. So essentially, you get a cost function parameterized by the neural network. Okay, so how are you going to design a neural network? There's a lot of flexibility. And so the design of neural network will reflect the modeler's modeling interest. Maybe you try to achieve better prediction accuracy while maintaining certain level of behavioral interoperability. Okay, interoperability. So that's maybe what's your goal. Maybe you just shoot for better prediction accuracy. So depending on your modeling interest, you can design the neural network in different ways. So for example, in one of our implementation, this is how we actually design the neural network. We design an attribute net. The input will be network features. So this includes, for example, for a particular path, the length of the path, the length of the path, capacity, number of intersection, number of left turn. So all the features. Okay, this feature will be neural network feature can be input to the neural network. And pass flow also the new input to the neural network because some of the attribute will be flow dependent, like travel. This is the attribute. And then we also design another neural network we call WeNet. So this learn about the weight. So it's learn about the traveler's preference over the learned attributes. Okay. So the input to the WeNet is going to be traveler's characteristics, for example, their origin, destination, where they live, where they go to. That's the basic information you can get. But if you have more information about their income, their gender, their value of time, etc. So whatever information you have, that can be the input. Okay, at the minimum, the OD pair. So that's going to be the input to the WeNet, and then the cost function, the pass cost is going to be a weighted sum of the attributes. So that's one of the design. Okay, so once you design the neural network, assuming the network has been trained, okay, you know the value. If they are trained, this is how you do the neural network-based network equilibrium analysis. And so you have once again, the contact information, traveler characteristic, and those feature at the input. And given the demand, you can have a feasible flow distributions. This is going to be input to the attribute net, and you have an attribute as output of the network. And then you also have the output from the WeNet, give you weight, and then you can compute the cost. So once you know the pass cost, it's easy for you to tell whether the particular feasible flow distribution is at equilibrium or not. If yes, you finish. If not, you go through this fixed point iteration, you update the past flow, you go through the process. Okay, so that's so-called the new network-based equilibrium analysis. The process is very similar to when you have a closed form past cost function, how you do the fixed point iterations. It's the same. Okay, but now how do you train this new network? So that's where the end-to-end learning play a role. And so how are you going to train a new network? At one end, let's you have observation of demand. So assuming you observe the demands. Let's assume you only have 3 samples. You also have the contact features. On the other end, you have the travel time observations, link travel time observation, right? So with the initial value of the weight for the new network, for each demand observation, you solve the corresponding VI, you prescribe the initial equilibrium pass flow, and then with that, you can estimate the link travel time. For each sample, you do that. And then you have all the estimated link travel time, you have observed link travel time. By comparing them, you can define a loss function. Right. So that's the forward propagation. And in the forward propagation, you solve a bunch of VI, but that's forward propagation. And then you can do the back propagation to compute the gradient of the loss function with respect to theta, with respect to the weight, and you update. Okay, this is the training process. It's similar to how you train a regular neural network. And this, you have forward propagation, you have backward propagation, right? So the training process essentially is to solve a mathematical program with equilibrium constraints. Okay, why? Because you want to, by determining this theta, you want to minimize the loss functions. For each observation you solve, you subject to this variational inequality, you solve the VI, and this essentially relate the flow with time, right? So this is the mathematical one with equilibrium constraint, the VI with power constraints, right? So that's essentially the training process is to solve this very big mathematical one with equilibrium constraints. So now is a good time for me to make connection between what we propose with some of the relevant research in the literatures. Okay. So for example, I can design my neural network to replicate a particular behavior model, like multinomial logic model. It's easy for you to design a neural network to replicate that. If you do that, then the learning problem becomes the model parameter calibration problem. So I can design a neural network to replicate most of the behavior model. And essentially, in a way, this proposed framework incorporates previous study and specialties. Okay. The second point is, if you get rid of the equilibrium constraints, the learning process is to train a regular neural network for flow prediction. Okay. So to elaborate the second point, let's look at the conventional approach of building neural network and to do traffic flow predictions. Okay, so the idea is like this. So you have some context feature, you have some flow observations, and then you train a neural network to create a mapping between the context feature and the flow observation. So once you train this network, you can predict the future flow. So that's essentially people does. Okay, a lot of previous study did this way. So conceptually, the underlying principle is, or assumption is, the distribution that generates the past flow observation is same as the distribution generating future flows. Okay, and we'll talk about in distribution prediction. So this can be justified for short-term prediction because you predict using the data from previously, you predict something in 15 minutes. So you can assume that the environment are the same, right? The underlying demand is the same and the network structure is the same. So therefore you can do in distribution prediction. What we are trying to do now is we train the data today and we want to predict something in 10, 15 years. And so you're doing prediction for future, a new environment. The network topology is going to change. The demand structure is going to change, right? You're trying to do auto distribution prediction. And so the regular network cannot do that. Regular neural network cannot do that. The recipe for our proposal is, instead of building this mapping from the feature to the flow, and we just want to learn about the choice preferences. Okay, we learn the mapping, we learn the choice preferences instead of flow distributions. Our assumption is the choice preference is going to remain the same for the future. So the preference you present today remain the same, and we follow the same preferences we predict the future. So that's the difference. Okay, that's a major difference between our proposal and conventional approach of neural network-based traffic flow predictions. And now, the training also different. I mentioned that for traditional, if we train a regular neural network, the forward propagation is easy because the neural network has a lot of explicit layer, and you have a very simple computation law or rules to link the input to output, right? Very simple for you to do forward propagation. For the backward propagation, you use auto differentiation. There's a very efficient algorithm for you to compute the gradient, right? You can train that very efficiently. And for here, even we have the same gigantic, we also have a neural network. But when you do the forward propagations, you have to solve a bunch of VI, and VI here essentially is an implicit layer. It's not explicit layer because by explicit, you have a computation rule to link input to output. And here you have to solve the VI, so we treat it as an implicit layer. Okay, so forward propagations. But when the backward propagations, you have to do the differentiation. You cannot use auto differentiation anymore because now you have to differentiate through this VI layer, or differentiate through the fixed point, or differentiate through the operation problem. So that's a challenge, right? So that's a challenge we have to overcome when we do the end-to-end learning in this setting. And so we propose some algorithm based on auto differentiation as well, and then other people propose other algorithm. But I believe that this remains a challenge and it will remain an active topic for the future. Because the success of this framework will depend on how efficient the training algorithm is. This will be very challenging because after all, we are solving a gigantic mathematical program with equilibrium constraints. That is a very difficult problem. Okay, but whatever we do, we try to leverage computational graph, and we try to leverage the auto differentiation from computational graph. Okay, so that's what we do. So we can, even we're solving a large-scale mathematical program with equilibrium constraints, and so we try to leverage the computational graph, and we try to have a more efficient solution to solve this problem. Okay. So now let's look at a particular example, and want to just deliver a proof of concept. So I mentioned that the example is going to be based on synthesized data. We use super networks. This is a very small size network. And then because we don't know the ground truth, so therefore we just assume a pretty weird cost function, okay? Very complicated cost function. And then we use this cost function to do traffic assignment to create testing data and training data and testing, right? So we created our ground truth. And then we use the training data to train our model, and then compare with two benchmarks. The two benchmarks will be traditional user equilibrium model, and for that, you assume people choose minimum travel time, choose the path with minimum travel time, so therefore there's no parameter in the category. And we're also assuming the stochastic user equilibrium, and in that situation, use multinomial logic model, you only need to choose category one parameter, which is dispersion parameter theta, right? But in our implementation, you have to calibrate 142 parameters. Okay, much more demanding. So therefore, if our proposal is properly proposed, and if the model is properly trained, our model should outperform those two benchmarks, simply because we have much more parameters in the category. Okay, so, and we look at first in distribution test, we train the model, we test the model. In distribution test, meaning that we train the model with the original network, and we test the model in the same network. Okay, so we look at different scenarios and compare with benchmark, compare with traditional UE, and we look at the mean absolute percent error. And then SUE, reduce the error by 18%. Okay, because you calibrate one parameter and you actually get better performance. But our end-to-end model reduced the error by 61, 62%, substantial improvement, which is expected because you have more parameter to calibrate. And also, we also do outer distribution tests, meaning that we modify the network and we test the model in a new environment. Okay, this we call outer distribution test. In this situation, interestingly, SUE actually perform worse than UE. And so the error actually increased by 9%. And our model continued to outperform, so reduced the error by 55%. Okay, that's just a simple example. We just want to deliver proof of concept. And so let's just show the potential of this proposed end-to-end learning framework. But we haven't answered, we need to answer the big question, which is, can this framework really learn about the preferences? How much confidence we have on this result, right? Can they really be learned? And in addition to choice preferences, there are also other unknown component you have to estimate, you have to calibrate when you build an equilibrium model, including link performance function, choice preferences, and demand functions. You need to calibrate them. Conceptually, I can approximate link function with another new network. I already proposed to approximate the choice preference using new network. I can also approximate demand function using another new network. So everything can be approximated by new network. By the way, when I say new network, I really, in a broad sense, this essentially what I mean is everything you can represent as a computational graph. If you use a model-based approach, if you really want a BPR function, I can represent BPR function using computational graph. I still treat it as a neural network. I can still calibrate the parameters, right? So, but anyway, that's assuming you just approximate them. You use model-free approach, you approximate all those three components using three different neural networks. And technically, the framework we just presented can be applied to train all those three different types of neural networks. The same approach works. For example, this is another case study, and we look at much larger network, Chicago sketch network, which is much larger. And so now instead of learning the choice preferences, we learn the demand function and link performance function. Okay, once again, we don't have a ground truth. We use our own ground truth by creating, for example, the inverse demand function, we assume some context-dependent exponential functions. So the context-dependent meaning that depends on the weather, depends on the week or day, the demand function is different. And link performance function, the same thing, context-dependent BPR functions. And with that, we solve the traffic assignment problem. We create testing data and training data. Okay, that's how we create the training data. But now with the training data, we train our model. We compare with the functional. The benchmark here is assuming you know the functional form. By magic power, you know the functional form. You don't know the functional form, right? But assuming you know the functional form, you only have 4 parameters to calibrate. And in this situation, the error is 3%. But without knowing anything, we train our neural network, we can reach about 10%, 9.5% error. Even our error is much larger than that one, but this is actually pretty impressive because that one is not a really fair comparison because we assume you know functional form, which is context dependent, and you only learn a few parameters. You only get 3%, and now I get 10%. So it's a pretty impressive result. But the question is, how much confidence do we have on this result? Can those components really be learned by the neural network? Okay, so that's motivated us to conduct some more formal analysis. And so the conclusion to our analysis is the end-to-end framework is impressive, meaning that when parameterized with sufficiently large neural network, the end-to-end learning framework can replicate any unique differentiable equilibrium state that saw well-posed variationally equal, which rely on strongly monotone, the cost function to being strongly monotone and with this continuous. Okay, so you can argue this pretty strong assumption, but with this strong assumption, we actually show that the framework can learn about those components. If you can parameterize the cost function with infinite depths of neural network. If you want to improve your accuracy, you can start from a finite network, smaller networks. If you really want to increase the accuracy, you use a wider, deeper network. But we have a theoretical guarantee that you can always reduce that error by using deeper and wider network. We also show that the framework can generalize to unobserved data when trained with sufficient observations. Okay, that's the outcome of formal analysis. And so how can we make such a conclusion? Is because we look at the error. The first error we look at is the expressivity error. Okay, so we show that the framework is expressive, and we show that if you parameterize the cost function using sufficiently large neural network, the expressivity error is upper bounded. So expressivity error is to measure the accuracy difference between the target model and the best possible parameterized model. Okay, so here essentially is about I want to approximate my cost function using neural network, and if I use a infinite depth of neural network, I can reach arbitrary accuracy between the prediction error from the target model and my model. So this is essentially expressivity error. And so this essentially means that you can always reduce this error by using a wider and deeper neural network. Okay, so that's the implication of this error band. Epsilon here is any arbitrarily small number. We also look at the generalization error, and you can see that error actually, the upper bound decreases with the sample size. And so which means that if you train this neural network, if you train the model using more samples, and you can reduce this generalization error. Okay, so this two results actually give us some confidence about the proposed end-to-end learning framework. Okay, because now we know that if you have a sufficient computational power, if you have sufficient observation, and you really can learn those unknown components with controllable accuracy. Okay, so that provides some theoretical foundation for the proposed framework, and this gives us some confidence about we can trust the learning outcome. Okay, so in summary, the centerpiece of our proposal is very simple. We just use deep neural network to represent choice preferences, demand function, and link performance function. Very simple. And if you want, you can go with model frame, which means that you do not pre-select any particular functional form, but you directly learn them from aggregate flow and Charlton data. So that's the first pillar. The second pillar is we built the VI in the neural network-based VI formulation to prescribe equilibrium, flow, distribution, and Charlton estimate. And then we encapsulate this VI at the implicit layer in the end-to-end framework. And then the neural network can be trained by comparing the estimate against empirical data. Okay, so that's essentially the takeaway message from my talk. 3 pillar and very simple. Okay, and so there's 2 points I want to highlight before I finish. The first one is because we try to learn the equilibrium state. the real system never settle into equilibrium. The observed flow are indeed not equilibrium flow. But for planning purpose, I mentioned that we need equilibrium as a benchmark against which we evaluate different plan, different options, right? So we can now observe equilibrium from flow, from observation, but here we actually, the training process actually learn a particular equilibrium state, okay? In addition to learning those unknown components, the cost function, the demand function, and the choice preferences, and then performance function, we actually learn a equilibrium state and use that state as a benchmark against which you compare different flows. That's the first point I want to highlight. The second point is, I mentioned that neural networks. So the framework really integrate model-based and model-free modeling approach within a single pipeline, because you do not have to go with model-free for each neural network. Okay, and if you have strong belief that I should use BPR function for the performance function, then you can represent BPR function using computational graph. You can still calibrate parameters. Okay, the same thing can be said for demand function or choice preference. And you can also go with hybrid approach, and you can use so-called physical informed neural networks. So quite some researchers actually study those type of hybrid models that you want to integrate the best for the model-free and choice model, the discrete choice model, into one model. So you do the combination between discrete choice model and the neural networks. So you have a better prediction error, a better prediction accuracy, while you can interpret the results. Okay, you have a behavioral interpretation from the model. You can definitely use this model and then incorporate it into our framework. Okay, and also because you don't have to train everything and use end-to-end learning framework. And if you have information, you can pre-train some of the component. You should do so. For example, if I have a trajectory data, I can actually pre-train the choice preferences, right? Because I have choice results, and I can train them, pre-train them, and then I leave the rest for end-to-end learning framework. In the example, we have an aggregate flow observation. We have aggregate time, right? We don't have a trajectory data. But if you have a trajectory data, you definitely can pre-train those choice preference and then leave the rest for end-to-end learning. So that's the second point I want to highlight. So my final words is, if you look at our competition modeling paradigm, not just equilibrium paradigms, and many other paradigms, technical theory, etc. So they were established at the time, like 50, 60 years ago, when there was insufficient empirical data and computational power. And after years of experience, our profession has improved those paradigms to make them work reasonably well in practice. That's we've been using this to do operation, to support operation and planning. I think it's time for us to really revisit those paradigms by leveraging the data, by leveraging the computation power, by leveraging the advancement in AI. So I believe a lot of research opportunity in this direction. I encourage the students in the audience to look into this direction. So with this, I conclude my talk. Thank you for your attention.
So much for wonderful. You are on time.
Yes,
Amazing. So, questions. Yeah, thank you, Professor Yin, for this really interesting presentation. It's mostly a new area for me, but I wonder, this baseline equilibrium that you talked about, is this transferable to a market that, say, has very high electrification penetration? So
yes.
I assume the choice changes a little bit, the choices that users make when they're driving EV versus internal combustion engine. I know you were looking at South Dakota, for example, probably it's not a hotspot for electrification yet, but I'm wondering if that affects the baseline equilibrium that you're talking about.
Yes, the choice, you would think the choice preference will be different for each other in EV, right? So you have linear example, and then you consider the driving distance, you consider my battery status, and you consider the availability of charging opportunities along the route. So that definitely affects your choice preference. And then, so our framework incorporates that. By example, when you have input features and you think about for one implementation, we have a VNet, right? So the input feature will include what type of vehicle you drive. You drive a regular vehicle, combustion engine vehicle, or electric vehicles, right? So you can actually learn of this. And then one of the feature, right. So here, the traveler characteristic can include what type of vehicle they drive, combustion engine drive vehicle or EV, right? And then for network feature here, you can think about the availability of charging station along the route. And so you definitely can incorporate those type of preference, and you can learn about the preference, and then that can support your plan. So certainly, you could argue that right now I don't have any EV in my traffic stream, so therefore I not be able to learn their behaviors, right? And then you have to sort of the beauty of this type of model is an automated process. So we envision planning as a service, meaning that I can automate the process of training and implementation in the crowd. Then I have the input trajectory data and this type of data automatically fed into my cloud. I continue to train the model, right? So therefore, when you have some traffic, some OEV in the traffic stream, you can gradually learn the preference of those drivers, and that can supplement the future. Yes, good question. Second.
We answered your question, the first question.
So I can dig a little.
But you can go and dig.
But
We were just joking that your last slide was just answering the question he had.
yeah, I was your first discussion point is my first question actually. So, but I want to dig a little bit deeper. So you mentioned about the ground truth, and actually the equilibrium may not exist even in a network. And then maybe a network is constantly evolving, and then there could be multiple equilibria that keep jumping around, right?
Yes.
So you actually observe what you are estimating is some sort of a fine combination of this equilibria that you observe. What I'm actually curious is that, first of all, is that how, in that regard, because of nonlinearity, it's hard to say that you are predicting better than some other models if you are really, the system is actually, there's no ground truth in a sense. You are actually targeting somewhere, you have two targets. You are actually hitting in the middle. I'm just wondering if you have any comments on that.
Right. So if you think about game theory, if you have a multiple equilibria, that's when game theory loses appeal, because you try to predict what's going to happen. You have a multiple equilibria, then multiple outcomes. You really cannot predict which one happens, right? So that's the challenge for game theory in general. Right. But then what I'm saying is this real system never settle into equilibrium, and equilibrium really is a mathematical construct. But we need equilibrium concept simply because there's no better alternative for us. The only reason why we need the equilibrium state, we needed the notion of equilibrium, is because, once again, we want to achieve apple-apple comparison. You really, when you compare two options, you really have to compare against a consistent benchmark. That benchmark is equilibrium state at this moment. Because if you think about it, do we have any better alternative? Because no matter what you do, you really have to against a consistent benchmark. Okay, so think about your alternatives. Your alternative could be, I have two options. I have many outcomes. I always compare with the best outcome. So that can be a consistent benchmark, meaning that I have plan A, under plan A, I predict multiple options, multiple outcomes. Among this multiple outcome, I choose the best one. And then for the plan B, I also predict multiple outcome. I choose the best one. I compare the best one, right? So the best case performance can be a consistent benchmark, or worst case performance a benchmark. So you can propose different type of benchmark.
Right.
Right. Okay. No matter, right, my point is, no matter what you propose, I can always find flaws with that benchmark. Because the benchmark have certain property. The first one is easy to compute. The equilibrium state, whatever benchmark you propose, has to be easy to compute. Secondly, you really have some kind of behavior from justification or foundation to support that notion of benchmark. Okay, so if you think about multi-property, the best alternative so far, still equilibrium state. Okay, still equilibrium state. So now, if you accept that, okay, equilibrium state is a mathematical construct we needed for fair comparison. So now, because the equilibrium state does not exist in reality, you have to learn it.
Exactly. Can you learn it?
Right.
Like maybe you can also learn the equilibrium.
That's what we learn.
I see.
We are learning. So essentially, the learning process is to learn the equilibrium state. And that equilibrium state, by the way, didn't exist in practice. It's just we learned it. Okay, we learn it, and then you use a benchmark to compare. Right.
Thank you.
Right.
I wondered, you have the two forms that you evaluated, one where you like know a particular functional form, another one where you sort of, I saw the comparison of the benchmarks in one of your slides. Can you do something where instead of inputting particular functional forms, you could input properties of what it comes up with? So for example, I'm not going to say that it's a BPR function, but I can say it should be convex, or
right.
Or can I say I want it to be logarithmically concave for demand?
Yes.
So you could input that.
Yes.
And
so
yeah.
So that's essentially when you regulate your neural network, and you can actually regulate the neural network in a way to reflect certain properties. If I want my neural network, if I want my cost function to be monotone, for example,
Yeah.
you can regulate that way. And so that's essentially what we do, because in order to ensure the VI to be well closed, we really have to regulate the neural network to satisfy that property.
Okay.
Yes.
My other quick question is, I think you had a theorem that you'd proved, a formal result on another one of the slides.
Which one?
Oh, it was about the uniqueness.
The uniqueness.
When the underlying problem has a unique equilibrium. Is that this can only converge to one set of parameter? Will your neural network, can you prove that it will uniquely converge to one set of
I cannot.
calibration?
I cannot,
Okay.
because the nature of the problem is a mathematical program with equilibrium constraint, right?
Right.
So for that type of problem, you don't even have a automatic condition for the optimum, right? Because there's so many local optimums. We never have any automatic condition for global optimum solutions.
Okay.
So you can, and in fact, for mathematical program with equilibrium constraint, you can only have strong, right, automatic condition, which you have strong stationary point. You don't really, there's no way we can find the optimum. So there's also optimization risk in this framework. Right.
Other questions?
Thank you.
No other questions?
I think we have some time to.
Okay.
I have a lot of questions.
Sure.
I'm really excited by the work. It's
Oh, thank you.
wonderful. If I may ask another question, actually following up on Professor Lee's question regarding the comparison you had with
This one, yes.
I was actually wondering, I understand that you had the ground truth, the BPR and so on, exponential demand function.
Right.
Then the benchmark is exactly using the same form.
Yes.
I'm actually wondering,
Right.
have you done this comparison? You change that do not use BPR, use the alternative BPR, but not the not the right one.
Yes.
And then just another parametric form.
Correct. We tried that.
That's not the truth.
Yeah, we tried
See
that.
how much you can.
Right. We tried that. So we have a paper, we do a bunch of comparison. I just select this two because in the interest of time, we did a lot of comparison. For example, you can assume, for example, linear function, right? Linear demand function and some convex, whatever function, and then you calibrate it. And then definitely the error going to be larger than end-to-end learning. And right, so it's really about the assumption you make. If you make closer to the ground truth, you have a better prediction rate. So that's, yeah, we did that.
So that, I guess, we will have, guys, a reception at the bridge, but Professor N would like to
Thank you
really
very much.
appreciate your visit with us.
Oh, thank you very much.
And, this is just to say thank you for your presentation.
Thank you very
being
much.
Our distinguished guest speaker.
Thank you very much. Very much.